Okay, so here we have a question from JEE Advanced 2025, Paper 2, Physics, question number 3. It is a single correct MCQ. Since I gave JEE Advanced 2025 this year itself, I felt that I would show how I solved this question in the exam, because in the exam I used the method which is not very commonly known and not many of you would have encountered this. So here basically we have two figures, figure 1, figure 2. Both are two separate cases involving simple harmonic motion. Here and in both cases we have two massless strings and one uniform rod. All right. And one more aspect is that we have to ignore gravity. Hence, the gravitational potential energy of the rod, gravitational potential energy of the rod will be ignored in this simple harmonic motion. Okay. So first we'll start by solving figure 1. I've drawn an enlarged diagram wherein the uniform rod has a small angular displacement by a small angle theta, due to which we will have a small linear displacement at point A, right, which is x1, as well as a small linear displacement at point O dash at x2, as you can see. Okay, so now first of all, we'll try finding out a relationship between x2 and x1. Via similarity of triangles, I have drawn an enlarged figure here of both the triangles. Through similarity of triangles, we can clearly see that O dash B is equal to 2AC, right? This means that x2 is equal to 2x1, okay? Therefore, we have found out a relationship between x2 and x1. This is important. Now, I'll show you my unusual method, which I solved. Most people solve this by finding out the force and torque and then solving. I have a slightly different method. I'm just going to state the total energy involved in this system. Total energy of the system is equal to half kx2 square, which is the spring potential energy of spring 2, plus half kx1 square, spring potential energy of spring 1, along with the kinetic energy of the rod, rotational kinetic energy of rod, half I omega square. Gravitational potential energy is neglected. Okay. Now, I'm going to input this equation in this. X2 equals to x1. E is equal to 5 by 2 kx1 square plus half I omega square. Is that right? Yeah, it is right. Now, here comes the innovative and new part, I would say. We know that in simple harmonic motion, the total energy of the system is always conserved. Total energy of a system is always constant. Hence, E is constant with respect to time. This means that dE by dt is 0. Hence, differentiating both LHS and RHS with respect to time, we get 0 is equal to 5 kx1 dx1 by dt. Is that right? Yeah, that's right. Plus I omega d omega by dt. Right. Now, as we all know, dx by dt is just velocity. Right. V is equal to dx by dt. Similarly, dx1 by dt is nothing but the velocity of this point A. Right. Is v1. Okay. Dx. I'm just gonna write v1 is equal to dx1 by dt. Okay. So v1 refers to the rate of change of this x1. It is the velocity of this point A, v1. I'm considering that. Okay, so I'll just erase that to save some space. Okay, yeah. So therefore, dx1 by dt is equal to v1. I'm considering that, which is the velocity of point A. Then we know that d omega by dt is angular acceleration alpha, well known. So 0 is equal to 5 kx1 v1 plus I omega alpha. Okay, now what I can do, I can express v1 in terms of omega. All right, I'll show you why I'm doing that. Now, as we know, v is equal to r omega. You must have learned this in circular motion. Similarly, v1 is equal to, what is r? R is L by 2, right? As you can see, OA, length of OA is L by 2, which acts as the radius in this case. So L by 2, because distance A, because this point A is here. A is located at a distance of L by 2 from O, which acts as the center for circular motion, right? This rod, it is performing rotational motion and it is hinged at this point O. So I'm considering that as a center. So R is equal to L by 2 and just omega. Remember, omega is constant for the entire rod. For all the particles of this rod, omega remains constant, but the linear velocity of each point depends upon the distance of the point from this hinge O. Okay, so omega is constant, L by 2 omega. Okay, so I'll just replace that. 0 is equal to 5k x1 L omega by 2 plus I omega alpha. Okay, now I can just cancel off omega since it's common on both sides. 0 is equal to 5. Now I'll write this a bit down. Okay, 0 is equal to 5k x1 L by 2 plus I alpha. Now I'm sure you must have gotten a brief idea of what I'm going to do in the next step. Let's see if you can guess. Okay, I'm just going to express x1 in terms of L and theta. As you know, in a circle, length of arc in a circle is equal to r theta. Well known, right? Where theta is in radians, obviously, but length of arc is equal to r theta. Since it is a small displacement, keep in mind small angular displacement for SHM always. So hence we can apply this concept of length of arc in terms of length of arc is equal to r theta. So considering the arc to be this small displacement x1, okay, we can say that x1 is equal to r theta, right? X1 is equal to r theta. What is r? As we solved here, r is equal to L by 2 theta, right? So I can write 0 is equal to 5 by 4 k L square theta. Is that right? 5 by 4, yes, k L square theta plus, now here I alpha. We know that I alpha is equal to tau, torque, right? Plus tau. I can rewrite this as, I'll write it here. Tau is equal to minus 5 by 4 k L square theta, right? And this is nothing but the equation of SHM. As we all know, SHM equation. Think, what is the equation of SHM? Tau is equal to minus k theta, the basic equation of angular SHM, if you want to be precise, right? This is the basic equation, which we have arrived at by a slightly different method. Now we can write alpha is equal to minus 5k L square theta by 4i. Hence we get omega is equal to 5 square root of 5k L square by 4i. Right? As we have all learned in SHM, this is the basics of SHM, which you must have learned in 11th grade. Therefore, time period in this case, T1, time period of oscillation, is equal to 2 pi by omega, 2 pi into 4 square root of 4i divided by 5k L square. Okay, done. So we have solved for T1. Time period of oscillation in this case is this. Okay, fine, nice. Let's move on to the second case. Okay, in this case, it is much simpler. Here we have both the springs attached at the same point A. Okay, so both the springs will have the same compression or elongation to be x1. Spring 1 has a compression of x1 and spring 2 has an elongation of x1, but x1 length is common for both. Once again, I'll write the total energy of system. E is equal to half I omega square, the rotational kinetic energy of the rod, plus half k x1 square, spring potential energy of spring 1, plus spring potential energy of spring 2, which is both the same. So I can just rewrite it as E is equal to half I omega square plus k x1 square, adding these two. All right. Now, as we all know, in SHM, the total energy of system is constant. dE by dt is 0, as explained above. Hence, differentiating both sides with respect to t. 0 is equal to I omega d omega by dt plus 2k x1 dx1 by dt. Is that correct? Yeah, it should be. Okay. Now, I omega d omega by dt is angular acceleration alpha plus 2k x1 dx1 by dt, as explained earlier, v1, velocity of this point A, as it is moving to and fro in SHM. Okay. Now once again, I can express v1 in terms of omega. v1 is equal to L by 2 omega, as explained above in the first case, I omega alpha plus k x1 L omega. Is that right? If I substitute that here, yeah, it is. Now I can just cancel omega from both sides, common. I alpha plus k x1 L, removing omega, yes. Now once again, I'll express x1 in terms of theta by the same length of arc concept. x1 is equal to r theta, which is L by 2 theta. So 0 is equal to, now I alpha is equal to torque. Once again, in the previous case, we solved all that. K L square theta by 2, right? So tau is equal to minus k L square theta by 2, which is the equation of SHM. Therefore, we have arrived at the equation of SHM. We have proved it is an SHM. So alpha is equal to minus KL square by 2I. Hence, omega is equal to square root of KL. No. I made a mistake. No, I was right. What am I doing? KL square by 2I. Right, this is omega. Okay, so the time period of oscillation in this case, 2 pi by omega 2I by KL square. So we have arrived at the time period of the second figure as well. Okay, this is the second figure and this is the first figure. Okay, now in the question they've asked f1 by f2 frequency, ratio of frequency. f1 by f2 is nothing but t2 by t1, since frequency is equal to 1 by time period, well known easy formula obviously. So if you take the ratios, we get the answer to be root of 5 by 2. This is the answer. Therefore f1 by f2 is equal to square root of 5 by 2, and this matches with option C, which is the answer. Thanks for watching.